Okay, so today I just today's talk will be in a slightly different format. It's on from the PowerPoint and more on the I think research done by Professor Simpson's group.
Yeah, actually today's lecture will be more overview.
Yes.
But I will also mention my own, a bit of my own.
Okay, so on behalf of all of us, even intermittently today, but finally maybe after tomorrow's talk more formally, I'd like to thank Efrat for this great set of talks. It's really amazing the way
Thank you.
Covered is such a large set of topics and in a so beautifully. And I'm hoping that the many students are going to be means it's almost like the topological condensed matter course have been partly done by her because of this very wonderful introduction. And that's and thank you for that. So with this brief introduction, I just continue.
Welcome to the fourth lecture. So today I'm going to give you an overview of the story of the nu equals 0 quantum Hall state in graphene, which is, as I already hinted in the previous lecture, it's a state of matter that is very different from the standard quantum Hall states, and it's unique to graphene or generally to Dirac materials, and it has to do with the fact that there is a Landau level at zero energy, which is very special and very unique. So this is the outline of my talk. I will start by some introduction, first of all, to the concept of quantum Hall ferromagnetism. Okay, so this is a topic that became very hot in the early 90s, already in connection with the standard quantum Hall effect, where it was realized that interactions are important even in the integer case. So I'll give some a brief introduction to that, and it will become relevant to my specific story. Then I will introduce the zero filling factor quantum Hall state and tell you about some overview of the first experiment. So first of all, it was observed experimentally. And then there were some theoretical ideas, and in at least the first years after its discovery, there was a confusion whether what would you expect it to be, either a perfect conductor or an insulator. The two options are very different, but then the experiments actually initially led to some controversy, but it was I think today we understand more about it. Then I will focus on a particular problem that arises from this discovery of the nu equals 0 state. So basically, as I'm going to show you and discuss today, it is a state of matter that can have different phases. Different phases and phase transitions between them. So it's not clear that it's just one state. It depends on the external conditions, and you can tune it to be something or the other. And there is both theory and experimental evidence that at least one type of phase transition you can see, and this is a transition from a phase that is called a canted antiferromagnet to a ferromagnet. So I'm going to explain all of this, what it means. Maybe now it's a bit obscure, and then I will discuss. This is the part where my own work comes. I will discuss edge modes. So we talked a lot about edge states, both in the integer and fractional, and in the nu equals 0 state you have different kind of edge states that are important or might be important for the transport, and there are some questions about them that came from the experiment. I'm going to discuss how the edge state structure also encodes the nature of the phase in the bulk. So once again, there is a bulk edge correspondence particular to this case. Okay, so and then most of what I'm going to tell you in these lines has to do with work that was done until like 10 years ago, but then there are some recent developments. As soon as everybody thought that we understand the nature of this state, some new evidence came from experiments that suggest that things are more complicated. Okay, so I'll let you know about
So just
some
a
new
very naive question. So at the very beginning, so I understood that how you explained this n equal to 0 quantum Hall states, but n equal to 0 for means zero energy for the Dirac fermions. What they actually mean? Like we have all these Zitterübigangers, things like that, right? For the trembling motions of the. So in that context, what is meant by zero energy of a Dirac fermion? Is that can it share?
It's just that the Fermi energy is at 0.
Okay, so the actual
the state. Okay, so the state of pristine graphene.
Okay.
If you don't gate it, it's that's the natural state of graphene. Okay.
So this has nothing to do with the zero. That there is some mechanism which suppresses the 0 point energy or anything like that.
No, it's not 0 point energy. It's energy 0.
No, that's what I'm telling. So
right.
There is no 0 point energy concept here.
No, we're talking about graphene, Dirac fermions, and the Fermi level is at. Okay, we define it as 0 because it's the particle Hall symmetric point.
Yeah, so it is
the charge neutrality point.
Okay, so it is essentially
0 energy is the is the charge neutrality point. Okay. Okay.
Okay.
Very good. Thanks for the question to clarify. Okay, so let me start first with the first point, the introduction to the quantum Hall ferromagnetism. Let's go back to the simplest example of the integer quantum Hall phase or state, where we already saw that to understand what's going on and explain the fundamental phenomena, you don't need to invoke interactions. It actually follows from a single particle picture. And the first stage to understand it is to solve for the energy spectrum, which are Landau levels. Okay, so this we already saw. But in addition, now I'm going to account for the fact that the electrons also have spin. Okay, so far I'm not talking about graphene, I'm talking about a standard 2D electron gas. The electrons have orbit and spin, and if we take into account the spin, each Landau level so in principle they could be, if the spin was completely insensitive to magnetic field, they would be twice degenerate, but there is a Zeeman effect, and it's characterized by some energy scale Ez that is typically smaller than h bar omega c, and that Zeeman energy splits each Landau levels into 2, and the ground state, if let's say if you're doping your system so that only 1/2 of the first Landau level is occupied, then all the electrons are spin polarized. Okay, so the ground state is spin polarized. Okay, and it's spin polarized because of a trivial thing, not because of ferromagnetism, because of just polarization by a magnetic field. Okay, So that's what the single particle picture tells you. And now you ask yourself, okay, this is my ground state. What are the excitations? What is the cheapest excitation I can make? In a single particle picture, it would be just a spin flip, okay? This would cost energy, if there were no interactions, the energy cost would be just the Zeeman energy, okay? Okay, fine, but unfortunately, or actually maybe fortunately, we do have Coulomb interactions. And the Coulomb interaction is a huge energy scale. It's very large. In fact, it is comparable to the cyclotron energy. It's much larger in many systems compared to the Zeeman energy. Okay. And what is the consequence of a Coulomb interaction? So this is an exercise of that I don't know, maybe you teach it in some quantum mechanics book. If you have particles, or let's say electrons with very low kinetic energy, and you introduce the Coulomb interaction, the Coulomb interaction are relatively strong compared to the kinetic energy, right? So they can introduce some many body effects, and one of the simplest many body effects that you get is you get ferromagnetism. Okay. Why do you get ferromagnetism? If there is a repulsive interaction, without doing any calculation, of course you can do some calculation that shows that you get an effective Heisenberg model for ferromagnetism, but without doing any calculation, it follows from the following effect: that electrons have repulsive interactions, so they want to avoid each other, but they are also fermions, and the Pauli exclusion basically forces their wave function to be orthogonal if they are close in space. So in order to allow them to minimize the Coulomb energy, they want to be polarized with the same spin. Okay, so the same spin. Well, yeah, it's basically, this is Hund's rule, but it can be traced back to Pauli exclusion. So effectively, ferromagnetism is generated from Coulomb forces, from electric forces, and it's very large, and that's also, by the way, the reason that iron is a ferromagnet at room temperature or much higher, has to do with the fact that the scale of the energy is really Coulomb energy and not some magnetic dipole or anything like that. Okay, so now, but however, we don't always see ferromagnetism in any material, because this would say that you always get it, right? Why do you not see it in like mundane metals? Iron is actually complicated, but in most cases you don't see ferromagnetism. The reason is that the kinetic energy is also large, and it competes with it, and basically does not support the order. However, if the kinetic energy is suppressed, then this ferromagnetism comes about, and the cases where you can easily see it is when you have a flat band. So when you have a flat band, effectively the kinetic energy is suppressed. Okay, so, and the interaction becomes the dominant. So basically, because of that reason, all that story is to tell you that a single spin flip in a quantum Hall state would not cost energy of Ez, but it would cost much higher energy, which is of order the Coulomb energy. Why is that? Because you are creating a domain wall, actually two domain walls between spin up and spin down, and that costs energy. Basically, in a ferromagnet, you have a notion called stiffness. You want the ground state is polarized, so all the spins are polarized in the same direction, and you can make some deviation from the collective polarization, but it has to be smooth and slow enough to minimize the energy. So it's basically like an elastic energy in a spring, right? So you can create, if you want to create a low energy excitation, it better not be just a single particle one, but it has to be something, some collective object that costs less energy, because the polarization is changing gradually. And this object is the skyrmion. Okay, so in fact, Shivaji Sondhi, who some of you know and also spoke in this place, in this forum, his PhD thesis was on that and became a very famous paper, and there were also some other works by Herb Fertig, Ellen McDonald, and others that discuss the same phenomena. So basically the claim was that the lowest energy charge excitation that you can have in a nu equal 1 quantum Hall state is not going to be a single spin flip, but rather a skyrmion, which is a spin texture that is depicted by this picture. What it does is actually you're basically spreading the spin flip over a finite radius, and you can compute its typical size, and it is a collective object where the spin deformation from up to down is happening gradually over many particles in such a way that if you account for the entire spin configuration, it covers the whole Bloch sphere. Okay, so if you integrate over the spin over the area of the skyrmion, you get actually a topological index that is called a Pontryagin number, and it's a kind of a Berry's phase, which basically is quantized to the value 1 or 4 pi, depending on how you define it, if the spin configuration covers the entire Bloch sphere. Okay, and interestingly,
so another very nice question.
Yeah.
So very similar mechanism happens in the case of the spin waves, right? Also, when you have the Gaussian mode.
Sorry. So spin waves are something, right? So spin wave is something else. It's So it's a smooth deformation,
right?
That can propagate and. But it's not topological. Okay,
right.
The skyrmion is a topological because once you have, and it can be, so you can have a static configuration that looks like this. Okay, it's not a spin wave. It's really you create a texture,
and it's gapped also.
And it's gapped, exactly. It's gapped, and its energy gap is smaller than the Coulomb energy. Okay, it's some geometric mean of the Coulomb energy and EZ, actually. Okay, so although this object is large in the sense that it contains many electrons, its energy cost is lower than flipping one electron. Okay. And that originates from the ferromagnetism. now there is
some kind of activation that is required to create these objects.
it's not activation energy, so it costs stiffness energy, okay, because there's a finite stiffness that prevents or limits the gradients in the direction of the spins, right? So
When we calculate the dynamics of this formation, how it would form spontaneously from scratch, or you take it as a given?
I take it as a given. I mean, it's really static, right? It's static.
From something.
Well, if you're talking about a system at equilibrium and you have a ground state and excitation, this will be the excitation. Of course, if you switch on the interaction at some time, maybe it will take time to develop. But if you just allow the system, this is just like in any many-body system, right? You can also ask about polarons or any kind of quasi-particles.
You have competing low energy excitations, and this one is the lowest energy.
This one is the lowest energy, exactly, you're right.
It can be calculated.
Yeah, yes, that's right. That's right. Now I want to stress one thing that is special. So of course a skyrmion is and all this physics I'm talking about in principle could appear in magnetic materials that where the band, the flat band comes from something else, not from quantum Hall physics. But in the context of quantum Hall, it has a very special significance because mathematically this Berry's phase, this spin texture is equivalent to some gauge field that is equivalent to a flux quantum. So having a single spin texture is equivalent to adding one more flux quantum to your system, okay? And because of that, because we are in the quantum Hall system, and the nature of the state is that electrons or charges are trying to adjust themselves to the number of flux quanta, this kind of excitation, if you make it, although it contains many electrons, its charge, its electric charge, is just the charge of a single electron, okay? So therefore the skyrmions and single electrons are the same in terms of counting charges. They contribute the same, but it is a collective object, and there is actually a formal expression here for the charge current in terms of the spin texture, and this operator, this n vector, unit vector, is the direction of the spin on the Bloch sphere. And mu nu lambda are indices which include time. So the j naught, which is just the density, is related to this vector product of yeah.
Oh, sorry. Hello. The spin is flipping.
Is flipping. So there is a spin that flips,
That flips.
But
I mean, that's the best thing. That's the least you can do.
One spin.
It's doing it to its surroundings.
Yeah. So
the surrounding is
so
a lot of
many
electrons.
There are a lot of electrons, exactly,
which are causing the spin flip.
No, so in the picture, the picture is schematic. So each arrow is one electron, if you like.
Right.
But there are many electrons. Okay, so you are flipping many electrons, but most of them are only a little bit. Okay.
Only a little bit.
Exactly.
But
right.
The full effect is a flip of one.
Yes. So that's why. Yeah, that's right. That's right. So exactly. So.
Because say.
Yeah. Right. Exactly. Right. Yeah.
We have three directions, right?
Sorry.
This n caps, these three are directions, right? And it's formula of,
It's the direction of the
but
spin.
n cap cross n cap, that should be zero, right? I mean, are these three different
No, these are gradients of n in different directions.
Okay.
So you have an epsilon. Yeah, it's just it's basically a Berry's phase.
Okay.
Okay. You have the anti-symmetric tensor, and the indices are time and two space directions. Okay.
I have a generic doubt. Like, how have you considered all the spins in the up direction? Like, we in a system, there are electrons with opposite spin also. To begin with, we are considering all the spins up in this state, and then we are seeing excitation energy.
So the ground state is ferromagnet. Ferromagnet is all the spins
up
in the same direction. That's the favored ground state, because then the stiffness energy is zero, right?
Because of magnetic field.
No, so again, I emphasize the polarization is not because, I mean, maybe the Zeeman energy help you choose the initial state, whether it's up or down, but it's not what controls the state. What controls it is Coulomb interaction. It's a much larger energy scale, and there is an effective Heisenberg term, S dot S, so that tries to polarize each electron with respect to its neighbors. Okay.
Exchange index.
Okay.
Is it worth thinking about this in terms of landscape or
So this is not a domain wall. It has a topology of. I mean, I'll get to domain walls as well, but this is a particular type of spin texture that covers the whole Bloch sphere. You can also have domain walls, but in any case, the energy, its energy gap is coming from the cost of making such a deformation in a perfect ferromagnet.
So if you were to image this over, let's say,
if you have a magnetic STM with magnetic tip, in principle, you should be able to image them. Yes.
But what we see
No, you'll see. If it's there, that's what you'll see. Actually, I mean, there were actually experiments that seeing it.
Shift experiment which show multiple speed which can result in
but how large?
It's a few it's of order 10 magnetic lengths. Now it depends on details, including the G factor of the material and so on, but it's bigger than a magnetic length. Okay. So it contains a number of electrons, maybe not a huge number, but it's yeah.
Okay. I had a little question. The Berry's phase is of a single electron or many of them?
It's a Berry's phase of. I mean, actually, let me go to my next slide, and I write a Hamiltonian. So you can actually rewrite the Hamiltonian or the Lagrangian, whatever your favorite.
Can I just ask one question?
Yeah.
Regarding the previous slide, you said that the ground state is a ferromagnetic state, which arises primarily because of Coulomb interaction, and the excited state is the Skyrmian one. So during this transition, how does the strength of the Coulomb interaction plays a role in the formation of Skyrmion? Does it increase or does it decrease?
So again, it's not something that forms suddenly. It's a many-body configuration that you can create. I mean, if you, for example, let me give you a concrete example. Suppose I'm injecting one charge into the system. okay, and the lowest Landau level, the spin polarized, is already occupied. What would you like to, where this charge will go? It will not go to a single electron, it will go to creating a skyrmion, okay? So it's just the lowest energy excitation. It's a many-body state. It's not described by a single particle wave function, okay? Okay, I hope I'm clear on that. So in fact, it is possible to write a Hamiltonian that is, what I wrote here is like the general paradigm for quantum Hall ferromagnets, which is expressed not in terms of single particles, but in terms of the collective field, which is the spin, okay? And the term that we already discussed extensively is the first term that comes from the Coulomb interactions initially, from the ferromagnetism, is just the stiffness, okay? So it is just trying to, it's actually basically the energy cost of a deformation. And that's just like in a Landau-Ginzburg theory, it's the same philosophy. And however, there is another energy term which is actually coming from the single particle physics, and it's just the Zeeman energy, okay? B dot S. Now, if you have a uniform magnetic field, this term is just trivial, okay? It just gives you B dot S, and B is constant. But if in some way you can generate in the lab a magnetic field or an effective magnetic field that is space dependent, this kind of a term can create something that plays the role of a kinetic energy. Okay, so it's very confusing. The interaction is the interaction is like a potential energy, and this term can be thought of something that has to do with the kinetic energy of the spins. And let me give you a concrete example. Okay, this is exactly the domain wall you mentioned before. Suppose I have, I can create a magnetic field that is not uniform. It changes sign over some, maybe over some length scale, doesn't matter, but there is a step. It goes from plus to minus. And even if this external field is changing rapidly, changing like a step function, the favored spin configuration or the ground state of this thing is now not going to be just a uniform ferromagnet, right? Because it's going, you are going to see a domain wall between a spin up polarized ferromagnet to a spin down polarized ferromagnet. What happens in between? Because of the huge cost of the exchange energy, there is this domain wall will not be as sharp as the external magnetic field. It will be a smooth domain wall, and the spin will flip across the boundary, across this domain wall. It will flip gradually over a length scale that is dictated by Js, or some combination of Js and the Zeeman energy, okay? So now interestingly, if you look at the middle of the domain wall, just, okay, here, the spin changes from up to down, and in the middle, it's in the XY plane. And at least in this problem, there is no energy cost of rotating it in the plane, in the XY plane. So there is an XY or a U1 symmetry for rotating the spin. And if you're looking at the static, you can create a static domain wall But such a static domain wall will break the symmetry spontaneously and choose some direction, X or Y or something, but there will be a gapless mode that can propagate along the domain wall, and that gapless mode is kind of a Goldstone mode, not really because it's in one dimension. It's a really one-dimensional object.
There is one
Yeah.
first planet.
Right. But it is a gapless mode that can propagate ballistically. So in fact, if it turns out that, as we'll see in graphene, on the boundary, you can create such a domain wall, and it leads to a special kind of edge state that comes from this. Okay, so this was just a general introduction.
Bubbles, or do they have structure?
No. So here, this is completely general. Okay, this is an academic exercise. I didn't tell you why would you have that, but now I'm coming to graphene, and that's where this physics can be.
Non-linear.
Yeah, basically, exactly. This is a nonlinear sigma model. That's right. In principle, you can also add some terms to it. You can do quantum fluctuations by looking at its field theory and so on. Yeah, that's right. Okay, and that's the language that is most useful to describe such systems, especially when you have non-uniform fields. Okay. I emphasize that so far I'm introducing it for a spin half. Okay, so I assume that the only discrete degree of freedom is spin half, but as we know, in graphene we have other flavors, and therefore you have much richer set of such models, and maybe you'll have to add indices for the type of spin flavors that are involved. Okay, so so as I said, there is a collective mode that can propagate, and it's one-dimensional. It travels along the domain wall. Okay, now I'm coming to graphene, and why is this story relevant to graphene? So this is an introduction that you already discussed. The special thing about graphene is that it has this Dirac band structure. Here you see actually the full band structure coming from tight binding, but close to the values K and K prime in the Brillouin zone, you have basically Dirac electrons, and you have two inequivalent Dirac cones, and in addition there is spin up and spin down, and altogether you have, you have 4 flavors, okay? And so in principle, you have an SU4 spin manifold, and there are lots of ways in which you can break it, okay? So quantum Hall ferromagnetism, if it's present due to interactions, can give you more options. And this is something, again, we saw already yesterday. The single particle picture just give you Landau levels that are following this law of the square root n, and you have a special Landau level at n equals 0, which is at exactly 0 energy, meaning at the Dirac point. And what you see in the right plot is actually the coming from the paper that won a Nobel Prize for the discovery of graphene, because it shows the quantum Hall effect steps, just what I discussed yesterday, okay? So this is now experimental data, not theory, okay? So you see the steps are not perfect, but they're very clear, And as you see, they follow the law that I discussed. The jump between them is 4 times E square over H, because there are 4 flavors. And near 0, you have a jump, or at doping 0, you have a jump from minus half to plus half of that thing, okay? So that's something that you can describe with the edge state picture that we already mentioned. So this is the...
I was still asking that really for some mechanism of plus up and minus up, right?
We'll get to it. So
Okay.
so far this is assuming degeneracy of spin and valley, but again, if we now focus on the 0 Landau level,
Right.
and we introduce the edges, okay, so now I have a ribbon of graphene with finite edges, and I'm plotting the spectrum as a function of guiding center, so it's in real space. Then the spectrum you get is what you see in this black figure, which is taken from Bray and Fertig's 2006 paper, okay? If you look at the higher Landau levels, you see that there is some splitting of the valley on the edge, but the energies always curve up, okay? They behave just like a regular quantum Hall effect, but the 0 Landau level has 2 branches of edge states that go, they are particle-like and Hall-like, and they're symmetric to each other, so that if you're focusing on the edge, you have right mover, one right mover and one left mover, or vice versa, depending on whether you are doping below or above the charge neutrality points. Now, this is assuming that there is no Zeeman splitting and no ferromagnetism, nothing. But now let us, still within the single particle picture, just see what Zeeman energy gives us, because of course it splits the spin into spin up and spin down, and it does it in a very trivial way. Okay, it just shifts all the levels by up or down, okay, or plus and minus half EZ. So this is what happens according to the single particle picture. If you zoom in on the edge, you are now going to get the spin up states. Their energies are shifted down, the spin down are shifted up, and near the edge you see that we are going to have a positive dispersion for spin up and negative dispersion for spin down, okay? And remember that the dispersion is dictating the group velocity or the direction of chirality of the edge modes or edge states. So if you're putting your energy, you still have a pristine graphene and the Fermi level is still at 0 energy, then on the edge you're going to get two chiral modes, one a right mover with spin up, left mover with spin down. This is exactly what we had in a topological insulator that is time reversal symmetric, okay? Here, there is no time reversal symmetry. This is in a magnetic field, but because of the, so first of all, there is a spin polarization in the bulk, right? Because if the Fermi energy is at 0, then in the bulk, only the spin up is occupied, so it's spin polarized. But at the edge, there is a crossing at 0 energy of right movers with spin up and left movers with spin down, and you get helical edge states And these helical states will give you a quantized conductance, a perfect conductance, okay? That's the expectation from this picture, if it's correct. So indeed, there was a paper by Abanin, Lee and Levitov that made this prediction and even did a concrete calculation of the what to expect for the 2-terminal conductance or 4-terminal conductance, and it suggests that you expect to see the quantum spin Hall effect. Okay, although this is not a topological insulator, it is graphene in and strong magnetic field. Okay, what is the expectation for the transport of such thing? It will be a perfect conductor, right? With no dissipation because of the helicity, and the 2-terminal conductance will be twice E square over H. That's the prediction. Okay. Now, however, this picture does not account for Coulomb interactions. What happens if you introduce Coulomb interactions? So that problem was also studied by Fertig and Louis Bray around the same time, 2006. You see there were many papers on this at the time, and they were considering what will the interactions do. And of course we already know from the story of the quantum Hall ferromagnetism in the standard quantum Hall effect that you will get ferromagnetism with stiffness, okay? And because of the stiffness energy that is much larger than Zeeman, you expect that such a picture will not be favored energetically because it corresponds to a sharp domain wall between a spin polarized bulk and the spin unpolarized bulk. You see in this crossing point, you're basically changing the lowest occupied level from spin up to spin down. So this is very costly, and what you're going to get is a smooth domain wall. Okay. So this is what interactions will do. You're going to get a smooth domain wall, and in this domain wall, there is, if you're thinking about it, now it's going to have this gapless mode that we already discussed. So you expect that there will be some collective mode that propagates, and it's better to describe it in terms of collective variables and not single electrons. And interestingly, in this collective variable, there is a direct relation, if you like, a locking between the current operator, the charge current, and the spin SZ are the same operator, okay? Because these are helical states, so all the spin ups are right movers, all the spin downs are left movers. So the difference between right and left movers is electric current, right? That's what dictates the current, but it's also the same as the difference between spin up and down, and that's SZ, okay? So spin and charge are locked to each other, okay? And similarly, there is a relation between charge density and the spin configuration in the XY plane. So there is going to be this gapless mode that I just mentioned in the previous slide is carrying charge. It carries an electric charge, and this electric charge has to do with this spin texture that covers the entire Bloch sphere, but it propagates. It's not a skyrmion, it's not a localized object. It spreads over an extended state, and that the dynamics of this, now it does have dynamics, the dynamics of this texture is going to give you a propagating collective mode, and it is going to be helical because of the locking between spin and chirality. And you can show that the field theory that describes it is once again a Lattinger liquid, but it's a so-called helical Lattinger liquids, okay? It's not chiral, but it's helical. Namely, what does it mean? It means that you cannot allow backscattering because it's locked to the spin, okay?
So what determines whether it will be a localized topological object or it will be a propagating modes? Is there a simple criteria or one has to check out all these possibilities and then come to the conclusion?
Yeah, so here because the domain wall geometry is such that you can make a rotation if you are exactly in the middle. Yeah, right, exactly. There will be the 1D dynamics will be gapless. Okay, it will be localized in the perpendicular direction, but along the domain wall you have a gapless mode. Okay, because you can make infinitesimally small deformation, and this thing can just propagate. Okay. So in fact, interestingly, this helical Lattinger liquid here is an object that is both a charge density mode and spin density, and they are related to each other. Okay, because spin and charge are locked to each other. Okay, so that's quite cool. Okay, because you can see a spin wave in charge transport measurement, in principle. Okay? All right. But
it's also robust, since if you put disorder around them, they'll survive.
Yes, for exactly the same reason. You can show that if you put impurities, an impurity cannot backscatter it because it cannot flip the spin. And even if you put spin impurities, that's a more subtle calculation, you can prove that it's to leading order, you cannot backscatter. Okay?
It's a very stupid question, but there is concept of spin charge separation in the Lattinger liquid.
But here there is no spin charge locking.
We have a spin charge locking.
So there's one flavor, if you like, which is both spin and charge. Okay. In fact, the relation in terms of quantum fields that are involved in the Lattinger liquid, the spin and the charge are locked in such a way that the spin is a dual description of is a dual field of the charge. Okay, that's just a mention for the experts, but yeah, it's very simple. It looks like a Lattinger liquid that has only a single degree of freedom. Okay, but it is such that you are not allowed to add to it backscattering terms that are backscattering. Okay. Now, however, so this is nice, but if I'm trying now to ask myself, okay, so what's the big deal about, what is the effect of interactions? I told you that without interactions, I have helical edge modes. They are single particle. Now I add interaction, and instead of single particle helical modes, I have a helical Lattinger liquid. What's the difference? No difference. So in terms of measuring conductance, they behave the same. They're both ballistic. The only difference is that this collective mode has a width, and if you could do local imaging, maybe you could see this domain wall. But if you just measure transport, you cannot distinguish. Okay? So the conclusion is the interaction should not change the fact, at least in this level, should not change the fact that it's a perfect conductor. Okay? That's what you expect from the theory. But then we're now in 2006, and then there were some experiments, okay? And the experiments saw the following. I'm mentioning the first experiment. The first one is the group of Gaim. I mean, Abanin is the first author, but actually, yeah, it's the Manchester group. And the second one is Fuan Ong's lab, okay? Chekelski was then, I think, a graduate student. And both of them saw the following thing, that if you apply a strong enough magnetic field, this, let me just go back to the old, here, the old, so while in the old quantum Hall, the first quantum Hall experiment showed that exactly at zero filling, there is no plateau, there is a jump between minus half to plus half. But of order Tesla, okay, yeah, and but if you now increase the magnetic field beyond 9 Tesla or something a bit higher, but around 9 Tesla I think is the typical field, then you start to develop a plateau at zero. So if you look at, maybe it's easier to look at the right hand side because it's a simpler figure. If you look at the lower panel, it shows sigma xy for different magnetic fields, and you see that in 8 Tesla it's kind of just starting, but it starts to develop a plateau at zero. And it looks like a regular quantum Hall plateau, but it's exactly at zero, okay? So there's no chirality here, obviously, but now you look at the longitudinal resistance, and you see that when the plateau develops at the strongest magnetic field, it becomes, there's a peak and not a dip in the resistance. So in fact, if you continue to increase the magnetic field further, you see a very high resistance at exactly zero filling. And in fact, also as a function of temperature, you see that it becomes higher and higher. So this is not a perfect conductor. On the contrary, it is an insulator, okay? With resistance that grows exponentially with both magnetic field and temperature, and lower temperature. So this is completely contradictory to what I told you, because not only it's not a perfect conductor, it is an insulator. So what is going on? And the answer came very, very early on, the realization that the effect of interaction that was considered by Fertig and Bray is very naive, because it doesn't account for the fact that you have a spin, you don't have a spin half system, you have SU4 symmetry, and ferromagnetism in the mundane sense that you just have polarized spin is not the only option, okay? There are other options to create a ground state that is ferromagnetic in a more generalized manifold of spin. So there was a lot of work on it. I think the earliest one was by Levitov et al. But there were many others. This was the earliest one, and the main point is that because of the SU4 symmetry, you have to do a interacting theory that accounts for many other optional ground states that might spontaneously break the SU4 symmetry. And there are many options. You can polarize the spin, you can polarize the valley, you can polarize some superposition of them. what do you get actually?
Neutral to normal.
Nu equal to. Yeah, okay, yeah, but here you really have, right, yeah, but here you have, you'll see that I'm now reporting perhaps the earliest work that provided a tractable theory that considers all the possibilities. Is a very nice work by Kharitonov from 2012. And what so let me first go back and mention we in principle we have, if we have a SU4 symmetry, we have 4 flavors that all of them are the same, okay? And the Coulomb interaction, if you just write the term in the Hamiltonian that describes Coulomb interaction, it's completely symmetric under all the indices. So it cannot distinguish between spin, valid, okay? And therefore, just Coulomb interaction, E square over R, is not enough to, is not helping in choosing which ground state you'll have, okay? You can have various ground states, they will all have the same energy. However, if you remember that when you discuss electron-electron interaction, the model that describes them is actually an effective model because we are projecting to the 0 Landau level, and the interaction is not just Coulomb, it has some structure to it, and you can in principle add to the calculation an interaction that is on a lattice scale, like Hubbard-like, okay? Short-range interaction, and this short-range interaction is sensitive to the lattice structure of graphene, okay? So it knows about the structure of the wave functions on the atomic scale. And if you are thinking of a model that you want to guess the simplest model that will capture its properties, this model will have at least 2 different parameters because it is not necessarily isotropic in the Valley degree of freedom. In the spin degree of freedom, it should be completely isotropic, like Heisenberg. But in the Valley, what is Valley? Valley has to do with, it originates from the lattice structure, okay? And there are differences in the structure factor of the interaction between tau z, tau being the Valley degree of freedom, tau z and tau xy. Okay, so I'm not writing here the Hamiltonian, you'll see it tomorrow.
Just curious to know, in this case you can write some CP3 type of nonlinear sigma model with different spin stiffness and the valley stiffness, and
yeah, you can do that, but okay. What Kharitonov did is actually starting from a microscopic Hamiltonian, but it had just, you know, the quantum Hall, writing the Hamiltonian in a quantum Hall basis plus interaction, and the interaction was kind of tau z plus tau xy, tau xy, okay? So it's basically it has this asymmetry, and there are actually 2 parameters that I don't know if you can see very well, but there's uz and u-perp. Right. Okay, u-perp is for xy, and theoretically you can just do Hartree-Fock, just mean field, okay? That's the calculation that leads to this, and look for the ground state, and you allow a phase diagram that allows these parameters to be anything you want, okay, from positive to negative, and that's what Kharitonov got. Let me go through. He gets 4 distinct phases. The two upper ones are spin polarized, but not completely. So the blue one, the one in the upper right corner, that's a ferromagnet. That's just the same ferromagnetic state that we guessed before. That state, if that was the ground state, would be a perfect conductor. So it's apparently not what you get unless you work hard to generate it. The other option, this I'll show you in the next slide, but theoretically there's some regime where you get it. Now there is the other option is a canted antiferromagnet. That's the one that is plotted in green. What is the antiferromagnet? It's almost an antiferromagnet. So on sublattice A and B, you have the spin is in the plane. They're trying to be opposite to each other, but there is some canting in the same direction. And this canting is induced because you do have a finite Zeeman energy. Okay? So that's a canted antiferromagnet. So that's the canted antiferromagnet, right? So
what angle is that?
How much it is? I'll show you in the next slide, but it depends on the parameters, okay? But you assume that the upper, the z direct, or the up is the direction of the external field.
And there's
okay?
No spin or thing.
No, it is sorry. So this is the direction of the magnetic field, and this is an XY plane. So there's breaking. Actually, this breaks U1 symmetry, right? Because the XY plane is completely symmetric, okay? So it chooses a direction in the XY plane.
Plane component of the spin. Is there an outplane component of the spin? Because the spin arrows are pointing the XY direction. It's a projection, or is this?
No. So let me again. What you see here is the XZ plane, okay? That's the XZ plane, and the X direction is arbitrarily chosen, okay? So in fact, what I'm plotting here is a state that actually has a Goldstone mode. Okay, it's a broken symmetry. The symmetry that is broken is U1. Okay? Okay, so the magnetic field, the orientation in the Z direction is determined by the magnetic field. So it breaks SU2 symmetry. Okay? All right. So that's the canted antiferromagnet. And now, however, there are two additional phases.
These pictures are not pointing out to the actual coordinate plane where actual plane where.
This, you mean the phase diagram is in parameters.
No, but
yeah.
I'm telling you, schematics which you put the
Yeah. So all these pictures are in, assuming this to be the Z direction, and the horizontal to be X or Y or something.
Looks like some protein structure.
It's actually okay. It's a chain of monkeys. I copied it from some. Okay, so let me just mention what are these two other phases. This phase that looks funny is called the Kekulé distortion. It's a Kekulé distortion. So basically, this picture is coming from Kekulé's original idea. Yeah, in his case, it was actually a snake. Right. But actually, what is? Let me mention what is the fundamental distinction between these two other phases to the upper ones. They are both of them are not spin polarized. So the real spin is a spin singlet. Okay, but it is charge ordered, okay? So the red one is a charge density wave. It's basically a broken, again, it's a spontaneously broken symmetry state where the electrons occupy just one sublattice, and the Kekulé distortion is a rather exotic kind of charge density phase where you create dimers on bonds, okay? And choosing a bond is actually breaking the translational symmetry of the lattice. So, and it is chosen spontaneously. So you create basically a lattice of dimers. This is just like in some frustrated spin systems you can get. Okay, so you get basically a lattice of singlets. And these singlet states, each of these blobs is describing a coherent state that is a superposition between sublattice A and sublattice B. Now there's something that I forgot
That's what
to...
shows.
Yeah, right, exactly. And now there's something I didn't mention yesterday. It turns out that when you solve the structure of the wave function for the quantum Hall state at the zero Landau level, valley and sublattice are the same. Okay, why is that? I mean, maybe let me just briefly remind that we got a Hamiltonian that has this form. Okay, for one valley, and for the other it's with A and A dagger interchange, and these are the harmonic oscillator state. Now if you want to have this was, let's say, HK. Now if you're looking for a spinor that will solve the Schrödinger equation with zero energy, it turns out that for this Hamiltonian it's going to be okay, phi naught is the harmonic oscillator first state, and this is just zero, okay? So, and this is sublattice A and B. So this is for valley K, and for valley K prime, where the A and A dagger interchange, you get that only B is occupied, okay? So in fact, these colors, the red and the blue in my figure, which are basically sublattice, are valleys, okay? So if you have a state that is a superposition of A and B, it's actually a valley coherent state.
These are the states on your edge.
No, these are all bulk states. This is theoretical phase diagram that comes from solving in Hartree-Fock the Hamiltonian of Kharitonov, okay? And however, you see that there are four distinct phases, and there are phase transitions between them, and in order to see the charge ordered phases, you need to have these parameters to be negative, and that's a question whether in repulsive interactions you can get it, but I'll get to it later, okay?
Experimental support.
Wait, so then that's exactly where I'm coming for. Okay, so this is what theory says, at least the most, the simplest theory you can say, that's like the minimal model that accounts for all the possible symmetries. Then it turns out that one of the predictions is that if the tinted antiferromagnet happens to be the correct ground state, there is in principle a way of tuning it into a ferromagnet and driving a transition. How do you do that? How do you change a canted antiferromagnet to a ferromagnet? All you need to do is to increase the canting angle, increase until it's polarized, right? And in fact, you can do it if you effectively strengthen the Zeeman energy, because the canting,
the two different spaces, they should smoothly go to each other.
yeah, they smoothly go to each other, and it's no, why is it? It's so it's actually okay. Let me tell you what. So in fact, what kind? It's kind of a second order phase transition. Okay, it's a second order phase transition, and it originates from exactly the effect that I'm describing now, which is if you write down an explicit expression for this canting angle psi, it's actually the ratio between the Zeeman energy and some interaction parameter. Now, if the interaction parameters are given, you cannot control them, at least not systematically, but the Zeeman energy you can effectively increase or decrease by tilting the magnetic field, because remember, we are in quantum Hall effect. There is a magnetic field perpendicular to the sample, but the Zeeman energy is proportional to the total magnetic field. It doesn't care about its direction in real space. So if you tilt it to maintain the perpendicular direction the same but increase the parallel, you can effectively tune up the ratio of Ez to GXY, and you see when it becomes, there is a critical value at which you get a full polarization, and that's a ferromagnet. Okay, so there is a smooth transition from a canted antiferromagnet to a ferromagnet.
These are active for These are active for
Completely Hartree-Fock, yeah. It's really a simple, and actually you can write down a nonlinear sigma model that follows from the Hartree-Fock, and you can very easily see why you get this solution, okay? For the angle, okay? You get a functional that is like cosine square plus cosine something, and right? It has a minimum at this value. Okay, so this is theory still. Now to the experiment. So there was a beautiful experiment in 2014 by Andrea Young, who at that time he was a postdoc at the lab of Pablo Herrio, how do you pronounce it? Pablo Herrio in MIT, and this was actually his job talk, Andrea's job talk, and now he's a professor in Santa Barbara. What he did is exactly what I just described. He took the sample that is in mu equals 0 state, and he measured two terminal conductance, okay? But he did it in the magnet lab in Florida, in very strong fields. You see, going up to 30-something Teslas. And he tuned his total field, so he did a measurement in such a way that you maintain the same perpendicular field. The magnetic field is tilted with respect to the sample, and you tune it so that the perpendicular component is the same, but the total field is increasing. So when it's
Why do we angle?
Of the field, it's not important. You can use it to parameterize. It's a way to parameterize Ez, okay? Actually, Ez over, so GXY, you can show from the theory is proportional to the perpendicular component of B. Right. So if you insist, you can convert it to an angle, but it's obviously it goes. This is the direction that it goes. So when you start from a relatively small Zeeman energy at charge neutrality, which is this point, okay? you get conductance is 0. It's an insulator, okay? If you go to finite doping of the graphene, you already get the quantum Hall state 2, okay? That's the usual quantum Hall plateau. But if we just focus on the zero state, it has 0 conductance, okay? It's an insulator, just like in the experiments I mentioned before.
You don't get it at the 0 doping. You get it with shifted.
The numbers here are not meaningful. The numbers, you mean that it's not at 0? That's because this is not the correct 0. Okay, it's just a trivial, there's some definition of the electrostatic environment or something like that, okay? Okay, so...
graphene samples?
Hmm?
Or the freestanding graphene samples?
No, these are, no, I think this is encapsulated in boron nitride, yeah.
So they have to compensate for some charge transfer from the samples?
Maybe, I mean, I don't remember the details of the setup for this particular thing, but it's, at the time there were high quality samples. Today we see much more. These are things that I'll show you tomorrow. We see a lot of things that you need clean samples for. But the challenging thing in this experiment is the magnetic field. It's very high. Okay, it's a lot of magnet lab time. Okay, but in any case, what's the main result? It's very beautiful, I think. You see that if you just focus at the conductance at 0 filling, it goes from 0 to a plateau at almost 2 times E square over H. Not quite, it seems to saturate a little bit below that, but that is actually an experimental proof, or at least it's consistent with the theoretical picture. Okay, and why is that? Because you are actually turning the canted antiferromagnet into a ferromagnet, and the ferromagnet has helical edge states. It's ballistic. It is a perfect conductor. Okay. Okay. So I see that I don't have. I only have like half an hour. So
ma'am, the conductance value at in the previous slide, the conductance value at very high magnetic field is more than 1. So,
it should be according to the theory, it should be 2 and not 1. Why 2? Because
it is
helical.
between 1 and 2. So why it is between 1 and 2?
Yeah, right. So, but it's closer to 2, right? It's closer to 2.
So it's giving.
I'll get to it in the end, because we have a theory which explains why it's not exactly at 2, but it should, theoretically it should be 2, not 1.
So why it is like at lower than 2 value, why it is giving that up type of spin?
Not sure I understood the question.
Okay. Okay. So it is not close to 2. So
it's not close to
2 value. It's like.
Yeah.
Then the spin up direction. How you are choosing?
From here you don't see this. You cannot see a spin. This is charge transport, right?
Okay.
This measurement has no information about the spin. I don't know. I mean, you just.
But you are plotting at the bottom different direction of.
Spin up, so then you write that.
I actually use the colors to denote the two extreme phases. So if I just focus on the 0 temperature behavior of so the canted antiferromagnetic phase should have G equals 0. Okay.
Okay.
The ferromagnet should have conductance 2. Now, what you get in between is with the resulting from finite temperature, finite, so there is some
off figure means it's a ferromagnetic.
Yeah.
And that's why I was asking, it is not close to 2, but still it's ferromagnetic. That's why I was asking.
Yeah, I'm saying that if it was perfect, if the experiment was perfect, we should see 2. Okay? Okay? Now, there is a reason why we don't see exactly 2, but it's still very close to it. Okay? It's still, it's almost a perfect conductance. Okay? Okay? So, all right. Okay, so, yeah.
Sorry, I missed this discussion, which was very important. The zero conductance. It's this. It's the lower.
Yeah, so
structure.
The zero conductance is what you get. I mean, this is an interpretation.
Yeah.
Because the ground state is a canted antiferromagnet, and the canted antiferromagnet does not have these ballistic edge modes. Okay. For a reason that I'll soon explain.
Okay.
But it is expected to be an insulator. Okay. So what I'm saying is, I mean, and this is now a theoretical understanding.
So at a very low temperature.
This is all at fixed temperature, which I don't remember, but I think it's something like 0.3 Kelvin or something like that. Okay, if you do it at much lower temperatures, maybe it will be sharper.
Or low magnetic fields.
The magnetic field goes from, again,
1.4 to 34
yeah.
Point something.
Very high. Very high magnetic field.
So the red piece is the ferromagnet. The red.
Yes, I mean that's the interpretation. I mean in the experimental curve, he used colors that are just some color scheme, but I adapted the color scheme to the theoretical interpretation of the extreme phases. Okay, there are only 2 phases here. Okay, and the reason that you don't see, I mean, theoretically, at zero temperature, you should see a jump from this to that, from 0 to 2. Okay,
0 to 2, yes.
Right.
But the structure is like this, going from this to that. No.
Yeah.
It is going.
Yes. Yes. I mean, it's an interpretation because we cannot. There is no at this point. There's no measurement that shows the configuration of the spin. It's electric transport, but the beautiful thing is that you can connect it to an interpretation in terms of the magnetic structure, okay? Because the charge behavior and the spin are linked to each other, okay?
But the one at 2, the conductance, the structure at 2.
You're asking about this?
No, the flat.
This is just a standard quantum Hall effect. This is when you have a doping. So the horizontal axis of the figure is the doping, basically the gate voltage. Right. So at charge neutral, the state that we are talking about is when your Fermi energy is exactly at the charge neutrality point. Okay? If you are increasing the Fermi energy to finite doping, then you get the first Landau level 1 and 2 and so on. Okay? And then you see the usual quantum Hall plateaus. Okay?
What's the meaning of ballistic?
Ballistic means that there is no backscattering. Okay? So that even though there are many impurities, the system is not perfect. You will see almost zero resistance and the current just flows. And the theory suggests that if you have a bulk ferromagnet, the edge modes have this helicity, so they cannot backscatter. Okay?
Really cool.
Okay, yeah, fine.
Quantum Hall effect.
Well, yeah. Okay, is it clear? That's okay. So this it looks like this experiment actually quite justfully gained Andrea his job at Santa Barbara, because it's really proof that it's actually a proof that the ground state of all the four phases I showed you, probably the ground state is a canted antiferromagnet, and if you work hard and tilt the field, you can maybe turn it into a ferromagnet. Okay? Okay, that's okay. So that you're already jumping to my last slide, but this is what was known in 2014. Yeah. Yeah. So that's the thing, that if you just increase the magnetic field and maintain the perpendicular direction, you cannot control separately the EZ and the G. This expression, EZ and GXY, both of them are going to be proportional to the magnetic field, so you don't change anything. So if you want to tune the ratio, you need to separate the total magnetic field from the perpendicular direction, which is the one that controls the orbital part and not the spin. Okay? That's why you need a tilted magnetic field. Okay? Good. Okay, so there are actually two things that I will not go through all my slides, because some of them are a little busy. Let me just give you the picture of what is the behavior. So we saw here several things, that there's some connection between the conductance and the spin configuration, but at this point I owe you an explanation, first of all, why the canted antiferromagnet is not a perfect conductor. Why wouldn't it have also some edge states that are protected? Why does it matter? Okay, that's one question. The second is, we saw that the perfect conductance is not perfect, and that also calls for a question: what causes it not to be perfect? Okay, so I want to briefly review one of my own papers from that time, and this is with Ganapati Murthy and Herb Fertig. I don't know if any of you know Ganapati. Is now in Kentucky, but yeah, he's Indian and he visits India very often. Okay, I will not go through the details. Let me just tell you the punchline, okay? And basically what we did was a detailed field theoretical description using this nonlinear sigma model for the nature of the edge modes in the two phases, and trying to see what happens to them when they evolve from a canted antiferromagnet to a ferromagnet. And what we found is that, okay, so actually let me first discuss, before I go to the edge, let me just mention the bulk. So in the bulk of a canted antiferromagnet, you have a gapless mode, because we already discussed this. So there is a canting in some where the z direction is dictated by the magnetic field, but the xy plane it's completely symmetric. Okay, so there is a Goldstone mode that is a gapless mode associated with rotation in the xy plane, and that gapless mode is kind of a gapless spin wave. Okay. On the other hand, in the ferromagnet, you don't have such mode, okay? You have a gap to any bulk excitation. Any bulk excitation has to overcome a gap, okay? So, on the other hand, on the edge, it's exactly the opposite, okay? So, what we found is and I really don't have time to explain it. If any of you want, you can come to me in private. But in the canted antiferromagnet, the edge state is kind of a modification of the domain wall state we discussed before, but with a very important correction, because because of the canting into the XY plane, the configuration of the spin that flips when you go through a domain wall is not covering the entire Bloch sphere. So it doesn't give you a full charge excitation. If you want to consider the lowest possible charge excitation close to the edge, it's going to be, in fact, something that is a skyrmion spread over the edge. And the way to visualize it is that you have a domain wall state and a vortex in the XY plane that that binds it such that together they complete it into a full texture of a single charge, a single topological charge, okay? So that's the structure. So there is some, if you want to make an edge mode that propagates on the edge, it must bind a vortex in the bulk, okay? And the distance between the edge and the core of this vortex is dependent on how deep you are inside the... Yes, it's a meron, exactly. It's actually a meron. Exactly, okay? So there is a meron coupled to the domain wall, and the distance between them depends on the parameters. And when you are starting to tune the Zeeman energy so that you change the tilt angle and you approach the ferromagnet, what happens is that the meron expands, and eventually in the limit that the canting angle is 0, it disappears and you just get the ferromagnetic domain wall, okay? So now in the ferromagnet, to create this deformation, you can get infinitesimally small energy because it corresponds to rotation in the XY plane alone. To create the edge mode in the canted antiferromagnet, you need to pay some stiffness energy, some finite stiffness energy, in order to create this meron. And as a result, there is an energy gap of the edge state, okay? The edge state in the canted antiferromagnet is gapped, and the gap, the value of the gap is related to magnetic stiffness, okay? So you can actually find an expression for it in terms of the stiffness, okay? It doesn't matter, there is some expression.
This means that the edge state is the conducting part. Is not always conducting.
The bulk is, first of all, the bulk in both cases, in both phases, in all the phases, is insulating. In fact, in all the quantum Hall states, the bulk is insulating. But the edge is not always conducting. That's exactly what I'm saying. That's exactly what distinguishes.
Evidence of that the edge is not conducting.
Yeah, I mean, that's what I'm saying. The nu equals 0. I mean, the first evidence was the old experiments I showed you in the beginning that showed that it's actually an insulator, right? Andrea Young was able to first show that you can turn it into conductor by inducing a transition to another phase. Okay, and okay, and yeah. So so basically, let me summarize our theory without going to any of the details. And by the way, they are in the papers. Of course, you can get the references and read them. So if I'm comparing the two phases, the canted antiferromagnet and ferromagnet, the edge modes in the canted antiferromagnet are gapped. There's an edge gap, and as you approach the transition, it goes down. Okay, it goes down, and the reason it goes down is that the stiffness energy becomes smaller and smaller. And then it vanishes in the ferromagnet, and you get a gapless mode, and the gapless mode is a perfect conductor. Now, on the other hand, in the bulk, it's exactly the opposite. In the bulk, the lowest energy excitations in the bulk are in the ferromagnet are spin waves with a gap. Okay, so they have an energy gap that is exactly given by the deviation from the critical value of the Zeeman energy. Whereas in the canted antiferromagnet, you have a Goldstone mode, you have a zero energy gapless mode, and it really originates from this degree of freedom that you can rotate the spins in the XY plane, and it's a broken U1 symmetry state. Okay, so the bulk and edge behave oppositely in terms of the spin excitations that are allowed, and now if we're coming back to the question that arose with regards to the ferromagnetic phase. So we convince ourselves that in the ferromagnet phase, if it's perfect, you should get perfect conductance, right? And it should be, G should be 2e square over h, but we see in the experiment that there is some deviation, and actually the problem is in this experiment they could not go beyond 35 or 34 Tesla. I mean, maybe the money ran out or the power ran out or whatever. So it could have been that you would approach it eventually, but it does look like it saturates. Okay. And going to lower temperature would be difficult. So,
Why low temperature?
Well, if you want to maintain low temperature and high magnetic field, that's very, very challenging. Okay, that's right. Like a different experimental setup, and okay. That's very hard to do, but I'm not saying that it's not possible, but usually to get to low temperatures, you need to put your sample in a dilution fridge if you want to really go to millikelvins, and that you usually do in your own lab. To go to 30 Tesla, you must use a public facility. Okay, nobody has 30 Tesla. In what?
There is Florida in its national identity.
Yeah, that's right. You have a few facilities in the world, and one of them is in Florida, and one in China, and
Grenoble also.
In Grenoble, yeah, that's right. So in any case, we wanted to have some systematic theory that explain why this conductance is not perfect, and it's important to mention that I told you that the edge states are helical, and therefore they cannot backscatter, because in order to backscatter you need to flip the spin. Okay, but it turns out that even if you have spin impurities, But static spin impurities, they are not enough to flip the spin. You can show that there is some conservation law as long as your bulk is spin polarized and spin is a good quantum number. That actually protects the helical edge states in such a way that static impurities actually are not enough to flip it, okay? And there are some papers by Leonid Glazman and others that actually, and Moshe Goldstein from Tel Aviv University also worked. Okay, it's actually not allowed, okay? So it's not that easy to spoil the perfect conduction, but remember what we have in the ferromagnetic phase. We do have spin wave excitations. The spin wave excitations apparently are able to flip the spin. And okay, this is just a caricature that describes them. And however, they are gapped. Okay, there is a small gap to these excitations, and they will give you some dissipation. Okay, I define this R is actually a resistance that is a deviation from the perfect conductance. That part is proportional to the rate of scattering via the spin waves. Okay, and this is something you can compute. So we have a work. This is with a former student, Pasha Tikhonov, who actually managed to do a very impressive, almost completely analytical calculation of this problem of having a helical 1D edge mode that is coupled to spin waves in the bulk. And
was the previous paper also analytical?
No, which paper?
The one just before this.
The one about the edge state. Yeah. So that was partly. That was also mostly analytical, but it was a different kind of. It wasn't. So in that paper, we just looked at some solving the spin configuration. Okay. And here it's calculation of transport. Calculating transport is a little more involved, but it turns out you can find a closed expression for the resistance. And in this expression, delta is the gap of the spin waves, which is parameterized by the Zeeman energy. So it's basically a measure of the Zeeman energy, and T is the temperature. So you get some functional form, and however, it's you see that it does tend to be exponentially suppressed when you go to zero temperature, but in the experimental regime, if you plot the conductance as a function of temperature, it looks very much like what you see in the experiment. Actually, the comparison is not is a bit confusing, because this is the theoretical curves are as a function of temperature for different delta, and different delta is like different magnetic fields. Okay, so there's no direct comparison. However, what you see is that if you are stopping at I don't know, 0.1 Kelvin, now I don't remember actually the actual temperature of the experiment, but if you are at finite temperature, of course at zero temperature it is 2, but at finite temperature it may deviate quite considerably from 2, and at least for the available data, this looks like a good explanation of what's going on. Okay, so so this completes the story of the canted antiferromagnet and ferromagnet. Everything looks appears to be consistent as much as data is available from transport. Is calculated using this this formula, which is, it's basically like an inverse Kubo formula. Okay, so yeah, okay, and it's very convenient for, especially for one-dimensional systems. Okay, okay, so so basically it seems like there are indeed the ground state of the nu equals 0 quantum Hall state in graphene is most likely a canted antiferromagnet. We don't have any imaging, spin-sensitive imaging to prove it, and it would be very hard to do because this this antiferromagnet is on a lattice scale. Okay, it's angstrom. You need something with resolution of angstrom to actually see it. But if you just look at the transport, it looks consistent.
Any exponent you can actually extract from the experimental.
Yeah, you can also do that, right? I mean, so we didn't study it, but actually, you know, that it is a second order phase transition, but the theory of Kharitonov is a mean field theory. So the transition is mean field. So there is no, I mean, probably in reality, there is some more interesting anomalous exponent, but I don't think, I'm not sure it's interesting, to be honest, to study it. Well, I think it captures like the main phenomena. But now I want to end with a surprise, or not a surprise, but new developments, because all this story ended around 10 years ago, okay, around slightly less than 10 years ago, and everybody agreed that this is the ground state of monolayer graphene in nu equals 0. Okay, but later on there were more experiments by different groups who do imaging, who do STM. Now in STM you see charge density. In just regular STM you see charge density, you don't see spin. And there were at least 2 papers, and actually if you look back in the literature, there were even older experiments that people sort of ignored. One was by Eva Andre and another by some Chinese group, but these were published in Science and Nature, so obviously everybody noticed them. So the left hand side is the group of Ali Yazdani at Princeton, and the second one is Benjamin Sassepe in France, and both of them did STM measurement of some high quality samples, I should say, and they went back and revisited the monolayer.
Does that imply low quality samples because STM is so common that they didn't see this?
Yeah, so you need, in order to see this, in order to make sense of the STM, to see a nice, really see configurations on atomic scale, you need a cleaner sample. Yeah, so but also, you know, it is not trivial. It sounds like a trivial thing, but it is It's not trivial to do this experiment and analyze it properly. But what I'm showing you is some figures from their papers, and what you see here in both of them, you see something that looks very much like the Kekule distortion. Okay, at least the version of it that is a bond ordered, like a bond. How do you call it? A dimer crystal kind of phase, and that's the one that I told you is very exotic, okay? And in fact, in Sasape's group, they also see by tuning the screening environment. So in his experiment, the special thing is he had a substrate that is STO, strontium titanate. It's a material with very high dielectric constant, and he can control the screening from very, very high screening to low screening, and by tuning it, it changes the image from actually in some regime he sees something that probably is not giving any charge density, but there is a regime of parameters where you see Kekule and you also see the charge density. Okay, so you clearly see charged ordered phases. And these are the two phases from the phase diagram. Yeah?
How about lattice reconstruction?
The lattice, you mean of the graphene? Oh, the lattice is so stiff. You need huge energies to distort it. Okay? This is like carbon atoms binding. No, it's very strong. Yeah.
This claim that graphene and the undulations.
No, the free graphene is a membrane, and it can have ripples. Okay, and that actually is a source of disorder because it's like a gauge field.
So what are the length of those diamond type of?
What is the what?
What is the size, the length of these diamonds?
This is the lattice. This is a lattice size.
Same as the graphene lattice.
Yes. It's really it's not a distortion of the lattice. It's a distortion of the electronic states on the lattice. Okay. But but you see very clearly this bond ordering, and it suggests that you can access these phases, okay, in the right samples and so on.
Is
and
supported by aberration calculations?
So again, the theory is mean field of a model that I will describe tomorrow, because tomorrow I'll talk about actually specific properties of that interaction model, but it's not a fancy calculation. It's really a simple.
What is asking some DFT or some type of more such calculation?
So DFT will not help you. So the thing here, you have to account properly for the interactions. Okay, so you can do Monte Carlo. You can no DFT. I mean, the band structure is trivial. It's all quantum Hall states. Okay, so the single particle problem is solved. The question is how to solve the interaction. But it looks like the mean field in quantum Hall very often gives you very good results that are consistent with Monte Carlo. But I want to mention, but the crux of the matter is that you assume something about the interaction model, okay? And what Kharitonov assumed is a simple model that has only two parameters. And what appears a little weird, if you say, okay, we believe this model and we believe the results, then where do you suppose to see the charge ordered states when both parameters UZ and U_perp are negative? Okay, which means if you trace them back to Coulomb energy, or to the interaction on the microscopic level, it suggests attractive interaction, okay? And actually it's quite understandable, because if you have attractive interaction, it's easy to imagine that you'll have charge density, right? Because you try to put electrons on the same sublattice. However, this is very strange, because we know that the dominant interaction is repulsive. So how can it be?
So I think of this as a Barrett's distortion.
It's kind of, but again, it's not a distortion of the lattice itself. It's a distortion of the electronic states. Yeah, the atoms are not right. So let me actually just summarize, because this slide is in fact a teaser for tomorrow's talk, okay? So let me summarize what I told you. First of all, I discussed the quantum Hall ferromagnetism, which suggests that there is some correlation between charge, flux, and spin textures, okay, in the quantum Hall states, and that particularly for the nu equals 0, we showed that there are collective edge modes. This is something I didn't have time to elaborate, but in fact they are like spin waves, but they're also spin and valley entangled, because the states have the sublattice and the valley are the same, and the spin and the sublattice are coming together in the anti-ferromagnet. So I didn't have time to get into this, but there are collective modes that carry both spin and charge, but their nature differs between the canted antiferromagnet and ferromagnetic case. In one case, it's you get an insulator because the edge states are gapped, whereas the ferromagnet is a conductor. And in fact, of all these phases that I mentioned, that's the only phase that is conducting. And it's possible to tune a transition between them, which shows in electric transport as a transition from an insulator to a perfect conductor. And finally, I showed you some evidence that although this story looks like it's a closed story, theory and experiments agree, there is evidence that the ground state has some charge ordered, okay? Now, this doesn't necessarily say that the canted antiferromagnet is wrong, okay? It may suggest that the ground state is a bit more complicated, and it may be a phase that has both spin order and charge order coexisting, okay? It doesn't exclude the possibility. What? Bond order, okay? Bond order is another name for the Kekulé distortion, okay? Because they are you select bonds, okay, and put dimers on them. So there is actually a nice a paper by Ganapati with Ankur Das and Ribu Kal.
Applied here, but unfortunately,
too bad. Too bad. Ankur, he's very good. Yeah.
Ribuka is now also effective charge, right?
Actually, he moved to Penn State. Unfortunately, he was in Lexington, and they lost him because of a two-body problem. Yeah, so anyway, these guys had a nice paper where they showed that if you consider a model for the interaction that is a little more complicated, you may get additional phases, and you can get a phase that is coexisting canted antiferromagnet and the bond order. In that case, you can reconcile all these experimental results together. Okay, so that's the story for the monolayer graphene. And tomorrow I'm going to discuss a multi-layer or a few layer graphene, and there you see some of these phenomena coming in an interesting way. Okay, so thank you for the attention.